So simplicial complexes have been defined purely as combinatorial objects, but the whole point is we want a topological space. Okay, so suppose sigma is a simplicial complex. We will define its what's called geometric realization. But first of all, it's a bit too abstract. We just have a collection of finite subsets. So let's identify vertices. These are singletons. Remember that given any subset at all, given any finite set in sigma, so if sigma is, let's say, v1 or v0 vn, then these sets also v0, the singletons, which we want to think of as the vertices, these are also elements of, well, I mean, if this belongs to the simplicial complex, so do these. Yeah, so the vertices of a simplex really belong. And similarly, a k-simplex is a set in sigma. So these have to be in sigma, of course. The vertices set in sigma of cardinality k plus 1 with k plus 1 elements. Okay, so far so good. Now we can associate to it a space. Remember what that is supposed to be, that if I have three vertices, let's call them v0, v1, v2, and these bound a simplex, then we should have the entire triangle that contains them, which means that if I take any convex linear combination of these, that should be contained. And what we do is we look at such formal linear combinations. So as a set, let's define mod sigma. Okay, so this is the set of all formal linear combinations, I equals 0 to n of ai vi. So this is a formal sum. So ai's are in real numbers, ai is non-negative real numbers, their sum is ai is 1, so it's a convex linear combination. And crucially, if I look at the vertices, that is the formal symbols which make these up, this is actually a simplex. This spans a simplex. Okay, so now if one of these coefficients becomes 0, then you could also write it as a linear combination dropping that vi. So the condition that subsimplices, subsets of a simplex are simplices is important for this to be consistent. Or you could make it consistent by artificial choices, but then it wouldn't be closed, maps wouldn't be continuous, etc. So we have got a set. Now topologically, so let's define the topology. Firstly, if V is finite, okay, and let's say cardinality of V is n, then mod sigma is a subset of R to the n, capital N here. It's simply formal linear combinations where we take 0 for the coefficients that are missing. Okay, so it's an element in R to the n, and hence sigma, so with subspace topology. And so we build from this something like a weak topology. Even with CW complexes, as I said, if they're finite, there's any reasonable topology coincides with any other. It's when they're infinite we have to be weak. So in this case we'll take weak by having direct limits. Okay, so now this was the first step. Now if W contained in V is finite, okay, then let's define sigma W. So this is equal to the subsets of sigma. I could write it as sigma intersection the power set of W. That is those that are subsets of sigma which are also in the subsets of W. So this is finite. Okay. So mod sigma W has topology as above. And what is more is clearly if W1, W2 contained in V are finite and W1 is contained in W2, then we have a map, by which I mean it's a function well defined and it's continuous with respect to the topologies given on these from mod sigma W1 to mod sigma W2. Namely, any simplex with vertices in W1 is a simplex in W2. So this is an inclusion map in fact. Okay, so now any simplex has finite support. It's contained with in fact with W being exactly its set of vertices. As a result, the union of these sigma W's as a set will give you all of sigma. Okay, or rather the union of mod sigma W's is all of sigma. So we define mod sigma as the direct limit over W, and I'm taking direct limit with the directed set of finite sets, and with inclusion being being the order, which makes it a directed system. So define mod sigma as the direct limit of mod sigma W. As I said, this is already true as a set, so as a topological space. So this is just like the weak topology, and in any case, the categorical property of direct limit is that if the composition with all inclusion maps is continuous, then you get a map on sigma W. So that you have a continuous function on sigma W, which is exactly like the weak topology. In the weak topology, we said that restriction to characteristic map, composition with characteristic maps is continuous. That's equivalent to saying restriction to finite unions of characteristic maps is continuous. Okay, so this was our geometric realization of which is having a topological space. Okay, so next we will turn to what the simplicial homology is, which won't directly use this geometric realization.